So in this section, we're going to look at fire and overheat protection, and this is all covered when you're looking up manuals, that kind of thing. Primarily is going to be in ATA Chapter 26, and whether you're looking at fire, no matter where it is, or overheat, whether it's pneumatic overheat or gear overheat or anything like that. This is fire and overheat protection, detection, all that. It's pulled into its own section. So, it's, sometimes people are like, oh, it's cargo fire. I'm going to go look in the cargo section. No, it's going to be in Chapter 26 rather than in compartment and fittings. So fire and overheat protection, it's got two main purposes going on here. The first is we need to detect one of these conditions, whether it's a fire or an overheat, and then ultimately we need to extinguish it or shut off the supply of materials that would be causing an overheat or a fire. So we can shut off, for a fire, we can shut off, get rid of fuel or get rid of oxygen or get rid of an ignition source. Or for like an overheat, if it's a duct overheat or a duct leak, we want to be able to shut off the flow of high temperature air through that ductwork that might be leaking, right? So there's a few requirements with fire and overheat protection that are key, and these are spelled out in the FARs. These are in Chapter 25, which is the section of the regulations that deals with larger transport aircraft construction, anything that's not a small airplane. And so there are 6 key design requirements that are specifically laid out in Chapter 25. And so the first of these is that we don't want false warnings, right? The boy who cried wolf, or yelling fire in a crowded theater, or indicating a fire on the airplane when there isn't one can lead to some pretty severe panic situations. Because oftentimes the actions that the crew has to take are fairly extensive, to the point of even ending the flight and having to land early. So, false warnings are a big deal. We want to know very quickly if there is a fire or an overheat situation. We want to be able to determine where it's at so that when that happens, the proper actions can be taken to put the fire out, to end the overheat situation in order to deal with it. As long as the fire or overheat is present, we want to have a continuous indication of that. So not only do we want to know, we want to know there is a fire or an overheat, but we want to know if we start doing, taking steps to fight that fire or to turn off the overheat, that they were effective and that it went out. Because if it continues to occur, there may be additional, more extreme steps that have to be taken by the crew or by the operator, even on the ground, to continue to make sure that there's, that things are safe for the passengers, for the crew, and for the aircraft itself. So that's when the fire is no longer present. There's some kind of an indication the fire's gone out, and that indication often can be a lack of continuous indication. So when we get a fire, we get some kind of a light or a bell or a noise, and that light stays on until the fire is actually put out. And then once the fire's out, that light shuts off, and that's our indication that the fire is out. Okay, so it's not necessarily a separate indication on top of the initial, hey, there's a fire. It's the, hey, there's a fire, no longer is telling you, hey, there's a fire. There have to be the abilities to test these systems. Most of them, or a lot of them, are tested every single flight, or at least once a day prior to flying, to make sure that, to test the integrity of the system and make sure that it is going to be able to indicate in the event of an actual emergency situation. And then they have to be damage resistant and damage tolerant so that they can still function. One, if in day-to-day service some kind of damage occurs, but also if during the course of indicating, a fire loop that has a fire indication system that is in the presence of fire, we don't want it to fail operationally because of that fire. So they have to be robust enough, and they have to be able to survive the fire or the overheat so that they can continue to indicate throughout the course of that emergency. So what are we looking for? It could be things like overheat, something gets too hot. Rate of rise detection, that is, something is getting too hot. Maybe it's not too hot yet, but the temperature is increasing so quickly that it's probably a pretty good likelihood that we're going to get into an overheat or a fire situation, right? That's that temperature building initially. Some aircraft have flame or infrared detection items on them. You all had the opportunity to trigger an infrared detector in lab. Smoke and optical detection. Okay, so in some areas we can sense temperature, other areas we can see temperature, or we can see smoke, which is the result of a fire, right? The combustion gases coming off of it. Carbon monoxide detection, not as common in large aircraft, right? All your small aircraft are going to have that, particularly if they have an exhaust muffler type heat system on them. But there's really not a lot of sources of carbon monoxide on transport aircraft, but it's possible. Combustible mixture detection, this is a relatively new one, and it's something that came about because of accidents. So this could be combustible mixture detection in some cases is in like the fuel tanks, where if you have a fuel tank with liquid fuel, it's not combustible. Jet fuel in its own right typically is not very combustible. It has to be atomized into a vapor and mixed with air. But you look at probably some of you studied the TWA Flight 800 accident, and that was a 747 that took off out of New York area and was flying to Europe. I can't remember the exact takeoff destination, but a transatlantic flight is fairly short for a 747. So they had fuel in the wing tanks, but they did not put any fuel in the center tank, the belly tank. There was still residual fuel in the belly tank. It mixed with the air, it got vaporized, and then a spark in that tank ignited it and basically caused a total loss of the aircraft, as well as everybody that was on board. It was just a few minutes after takeoff. And so that was so you'll start to see some of these combustible mixture detection. Other areas where you might see combustible mixture detection is on cargo aircraft that are designed to be carrying hazardous materials. And there's regulations surrounding that as well in order to limit the potential for a cargo aircraft to be damaged. There's quite a few restrictions about how you transport hazardous materials and potentially explosive materials on aircraft. One that I don't have here kind of goes along with it, similar to carbon monoxide detection, is a carbon dioxide detection system. These weren't very common, but they did rear their head during the COVID pandemic. Anyone have any idea why? Yeah. Because of masks? Nope. Nope. It's more of a cargo airplane thing. Any idea? Or planes converted to cargo? So at the early rollout of the vaccines, anyone remember anything about the COVID vaccines? They had to be kept really cold. How do you keep them cold on an airplane? Dry ice. What is dry ice? Frozen carbon dioxide. What happens is all that dry ice starts to melt inside of an enclosed airplane. It gets tasty. It doesn't, I've seen blow, it's not going to blow up, but what it's going to do is displace all the oxygen that's in the airplane. What happens to the flight crew that's flying that plane full of vaccine coolers that have dry ice in them if they all start leaking carbon dioxide? They take a nap, right? They take a long enough nap that the plane flies into the ground potentially. So, there is carbon dioxide detection out there as well. A buddy of mine's a 7.6 first officer at United. He flew some of the planes that they needed planes. United didn't have cargo planes. They actually made shipping containers they could strap into the seats. So he flew planes full of basically cooler boxes where every single seat had a cooler box strapped in it over between Europe and the United States in order to do that. And normally there's limits to the amount of dry ice that can be packed on a plane. They had to get special waivers from the FAA, and they had to put carbon dioxide detectors in the cabin in order to show they could operate those safely under those conditions, those abnormal conditions. So different areas on the airplane are monitored, but there's kind of some standard areas that are normally monitored. So for fire, areas that could have fire are areas where we have fuel sources, and it doesn't have to be jet fuel. Fuel can be hydraulic fluid, fuel can be engine oil, fuel can be cardboard, fuel can be clothing and luggage, right? So a fuel source. So areas where we have those fuel sources, engines obviously, hydraulic fluid and oil and fuel, and who knows what else. Cargo holds, right? You got all the stuff down there. People put their lithium ion batteries in their checked luggage, even though it says you're not supposed to, right? And then lithium ion battery goes, what do they call that? Thermal runaway or something? No, I've heard some other terms for it. And then starts to light off everybody's clothing, right? Lavatories. Okay. Why the lavatory? Why is there combustible issues in lavatories? Methane. Hopefully there's not a high enough concentration of methane. But up in the front here, I heard people mention something about smoking. Somebody is just dying for a cigarette after they've been on a flight for 12 hours and they think they can go in the bathroom and light one up. You can't. There's a smoke detector in there. But then the smoke detector goes off and they've got this lit cigarette and they're going to try to get rid of it so they can't get caught, right? They're not going to get caught. So where are they going to throw it, potentially? Into the trash. What's in the trash? Lots of paper. Everyone uses a paper towel, right? We don't want to light the paper. Planes have crashed because of lavatory trash receptacle fires when people threw cigarettes in them. Wouldn't it make sense not to light up a cigarette on the airplane when it's illegal in the first place? Oh, okay, fair enough. I mean, I've had two. My kids are pretty good usually, but I totally can understand that. I don't know. Go like binge eat cookies out of the snack basket or something. But lavatory, in fact, if you travel in the United States, you'll see there's still no smoking signs on every airplane. And if you look, there's still an ashtray next to every single lavatory. And that's not by mistake. That's not by happenstance. That is a federal regulation that you have to have an ashtray so that if somebody does happen to light up a cigarette, there's somewhere to put it besides putting it in the toilet. I don't know. It's posted next to there's a placard next to the smoke alarms that usually tell you. I think it's like at least $1,000 fine. The $1,000 fine is minimal. The issue is that the plane may have to divert. If you cause a diversion of an aircraft by your own actions, the airline can come after you for the costs of diverting that flight. And that gets real pricey real fast. Okay. There's fuel issues, there's crew scheduling issues, there's all the delays. They got to pay all those passengers for delays or rescheduling. Right, that civil penalty can add up very, very quickly. What's that? Yeah, so you got to buy hotel rooms for 400 people because you can't fly them out from wherever you divert to for the night. So smoke, cargo holds, again, lavatory, and the cabin area have smoke, various ways of seeing smoke, and they may be smoke detectors. Most cabins with passengers don't have smoke detectors, but a cabin with 400 people probably has 400 smoke detectors on board, right? You can see it potentially, you can smell it, that kind of thing, so that kind of falls in that category. Overheat, we can see in areas like ducting, areas where you're going to have bleed air. So the ducting that carries bleed air throughout the aircraft, the wings that have bleed air for anti-ice, cargo holds can have heat stuff because of that going to them. And then landing gear, if our brakes get too hot, or if a burst tire or something like that, that can cause heat issues. So if you get a fire on the landing gear or an overheat on the landing gear, you want to know that. Because normally, landing gear sucked up in the belly, that's right next to, what is the gear, when you look at the 727, what is right next to the gear when it's sucked up in the belly right there? There's some fuel tanks. More critical than that. The APU is usually not even in the belly area anymore. No, not the air cycle machine. Think more structural. What runs right through that landing gear bay? Your main spars. If those get too hot and they start to get weak, your wings no longer stay on your airplane. So if you get a big fire down in that landing gear bay, you don't want to weaken the structure. And then I talked about combustible mixture, and that's primarily cargo holds, especially if you're carrying hazmat materials that could lead to combustion. And now fuel tanks. So what they're doing with fuel, this goes back to the asynchronous fuel lecture. What are they putting in fuel tanks to prevent this combustible mixture? Who picked up on that? An inert gas system. You have it's called a nitrogen generator. It takes air in, basically strips the oxygen out of it, and it pumps nitrogen, nearly pure nitrogen, 99% nitrogen into the tanks in place of the air that was in there. And that was a result of that TWA 800 flight. Okay. So looking at what makes up the detection part of it, here are some of the common components we'll see. So sensing elements, there's various types of sensing elements, and you saw these, you got to trigger them in lab. So sensing loops of various types, and loops can come in different flavors. They can be, you've heard of Fenwal and Kitty, they can be the chemical eutectic salt type, which is what those are. They can also be a trapped gas loop that works off of pressure. So it's a thin, a little straw essentially, and as it heats up, the gas inside of it, pressure increases, and it'll trigger a switch. It can be spot sensors or optical detectors like our infrared detector. That's going to feed into some kind of a device that is going to provide control and monitoring function. And on your modern aircraft today, that's almost always going to be a computer. Back in the day, it was like logic circuits, relays, and that kind of thing. But anything that you work on modern, it's going to be computer-based. And there's going to be multiple computers for redundancy. Typically at least 2, sometimes 3 computers that are all doing the same job. They're looking at the same thing. But that way, if one goes bad, you don't have that. We got to have those indication areas, so we can have things like lights. Lights can come on, messages on ICAST, and then oral warning. What kind of oral warnings might we see? Or hear, I should say, because oral means audible. So you got the bell. Everyone's ears are probably still ringing from when we did the 727 fire bell, right? Especially whoever had a stand in the entryway there, right above their head. Okay, Jeremiah, yeah. Surprised you can hear me. What else? What else might you have on some newer aircraft, do you think? Fire, you'll have voice type messages. In fact, it won't even say fire, it'll actually tell you where the fire is. Engine fire, left engine fire, gear bay, overheat, right? So, okay. And then test circuitry, that's that built-in test equipment they're required to have to check the integrity of the system. As you can see here, there's a test switch, what it might do, in some cases, they may ground out a loop, or it might check continuity end-to-end to make sure there's no breaks in it. So there's different ways that these systems can do continuity. Older planes, like the oldest planes I had to work on, we would have actually 2 test switches for a loop. So one of them would put a ground on the center conductor of the loop, which triggers a fire warning, right? So we could show, okay, it'll trigger a fire warning. The other one sends a current, it's almost like an ohm meter from end to end. It says, okay, your loops don't have any breaks in them. Okay, from end to end. You can see the loop makes a circle like this. And so for like this computer, if it sees a ground, normally it would see a ground on both ends, right? If we hook a ground up here, put a ground up here at the top, you would see that ground back at the computer. But if you had a break in the loop, say it got physically broken or there were multiple loops connected in series and they got disconnected, say it was broken here and we got a ground here, it would still send the ground to this end, right? You wouldn't see it on that end. That's okay, it can still give an indication. But say the loop was disconnected here and here. Now what happens if you get a ground or an indication up here? Did you get any kind of an indication? Nope. So one of the tests would be, it makes sure that there's continuity end to end to make sure you don't have two potential breaks somewhere in that loop that would cause there to be a non-sensing portion of it. Okay. So we had test switches. We had to go to the test side to make sure it would indicate a fire. We had to go to the integrity side to make sure it would go end to end. Later airplanes I worked on, you had to do that for each loop. You sit there. The newer airplanes I worked on, you sat down in the pilot seat, you reached up, and what used to be a big panel in the older version of the airplane was still a big panel. It had one push button in the middle of it. And you hit that, and it automatically tested every fire and overheat system on the airplane. The computer just ran all the text, and then you would get a message on the ICAS whether, fire system okay. Or it would say fire system fault, and then it would list what the fault was in. So that's what you'll see in newer aircraft. Our various sensing element. So this is the eutectic salt type shown here, continuous loop eutectic salt. Are these top two up here. Typically, when we have these installed in an area, there are two loops running parallel with each other. And that provides a couple things. So first off, damage and break tolerant. That's what I was talking about. A break anywhere in the middle, it can still sense at either end. Okay, two breaks in the middle. Now you've got a dead section somewhere. So that's where we check the integrity end to end on a regular basis. Now, so that's the damage and break tolerance. Redundancy, two loops like this. Under normal operation, you guys saw two loops. When we were in the 727, how were the two loops identified for the engines? Anyone remember? It's a panel right on the back wall, kind of next to the door, very bottom. Anyone remember what was on that panel for the engines? There's a switch that's got an A position, a B position, or where's it normally left? The center, A and B. When it's in an A and B mode like that, and that's all managed by a computer now, by the way, you don't have those switches anymore. But when it's in the normal mode, normal operation, which is A-B or A and B, to get a fire indication, it has to see a fire in both loops. And that's that we want to prevent any kind of a false indication. So under normal operation, if one loop, the salt breaks down in, it's got this eutectic salt between the center conductor and the ground, if that, or between the two wires, if that salt were to break down and cause, just a ground somewhere in one loop, say it was in element 1 here, we wouldn't want that to set off a fire warning, right? But it would be something we would pick up during our bite check, or on new aircraft with ICAS, it might give a, left engine loop A caution. It tells you that loop, something's wrong with it, it's degraded. Now, if you know that one of those two loops is bad, if A goes bad or B goes bad, that's why on the 727, that's why there's that switch that you can select A or you can select just B. And in the new computer, airplanes now, if they've got the computer system, it does its bite check, it sees that, it will automatically go into a reversionary status where it only is looking at one loop. So that's what you do when you switch that switch. If you switch it to A, you're telling the fire system on the airplane, only look at loop A, ignore B. What that means, though, is if you've lost that kind of check and balance. So there's a higher likelihood of a false alarm when you're running on just a single loop. So why do we have the option to run on just a single loop? What's the reason behind that? Why not just say, well, if one of the loops is bad, we need to repair it right away? Well, they're normally both in operation, and you can use kind of the one or the other as the backup. Why do we have that backup? Why would we do it that way? We say, okay, we're going to give up some of that check and balance. We're going to make it so it's more, it's more prone to having a false alarm. Why are we okay with that? What's that going to allow the airplane to do? What's that going to allow our operation to do? It's going to allow us to keep flying until we can get that plane into a location where maintenance can be performed. Okay, it's called a deferral, a deferred maintenance action. It wouldn't put it out of service. There's a couple of things for that. One, schedule's built all day. You don't want to interrupt the schedule if you can avoid it. The FAA says, yeah, for 3 to 5 days, maybe it's fine. Okay, yeah, there might be a higher likelihood of a false alarm, but it's still a very low likelihood over a short period of time, right? The other part might be you discover that loop B is bad when you're in Bemidji, Minnesota, which is this little tiny single strip airport, right? There's no maintenance base there. There's nothing there. If you didn't have that ability, you would have to get a ferry flight permit to move the plane. So it allows you to continue to fly the plane and continue to fly passengers in many cases. Okay, you can defer the maintenance. So that's why we have multiple loops. It provides that check and balance. It also gives us that, it increases the dispatchability of the aircraft. Okay. We've got the two main types, and you've probably seen these before. We've got our what's known as a Fenwal type, single conductor in the center, eutectic salt that provides an insulation until it gets hot, at which point it allows conduction to the Inconel tube on the outside that supplies the ground. The Kitty style works similar. It's got two wires in the middle, and it's looking for continuity between the two of them or to the sheath potentially. However, Fenwal, nowadays, Fenwal makes the Kitty style, Kitty makes the Fenwal style. There's other companies, everyone makes everything now. They're just called that because that's who developed them originally. How do you keep them straight? How do you know which one's which if you're trying to remember? Anyone? There's my loop, right in the name. The two circles in Kitty. There's my two wires. That's how I always remember them. Okay. Fenwal's the single, Kitty's got the two, like the two Ds. Yes, good. I try. So Kitty, you can think of it like the two Ds in the middle of the name. Okay. Kitty style versus Fenwal style. But I have seen, you'll go out there, you'll see single wire loops made by Kitty. You'll see dual wire loops nowadays made by Fenwal. You'll see spot detectors made by Kitty. You'll see spot detectors made by Fenwal. Yeah. Because Fenwal came up with one wire and Kitty made two. And at one time, they had patents on them. So at one time, only Fenwal could make that style, and only Kitty could make this style. But those patents have since expired long ago. These were developed fairly early on. And so now everyone makes everything, and they just bid out, a project, and who knows. And they can be used as fire loops where they trigger at very high temperatures, 1,000 degrees Fahrenheit. They can also be used as overheat loops where they change the composition of the eutectic salt or the thermistor material, and it activates at, say, 400 degrees if for like a bleed leak, or 300 degrees or something like that. So they can make these in different different trigger points. And so just be careful. Just because two loops look the same doesn't mean that they're interchangeable. You always want to check part numbers and that kind of thing. Okay. So again, back to, here's that setup. Okay. We also have pneumatic loops I was talking about, where it's essentially a tube filled with a gas. Here they use helium gas. There can be others, okay? But what happens here is they're pressure-based, and so there is what's called a hydrogen-charged core with helium gas. When these get hot, that hydrogen core material releases hydrogen gas into the helium. Now you have more gas trying to take the same space, and that will cause a pressure increase inside the loop. And it basically just pushes on a little switch down here in the what they call the responder assembly, the base of it. Okay, that gas pushing on there does it. Now, there's actually two switches here. So one is the alarm switch, and this is shown in the alarm mode. So right now there's pressure pushing it closed. Okay. The other one is there's an integrity switch, and this is held by that helium gas. It's a low pressure. And it provides, so what's going to happen is, under normal circumstances, this is open, and you're going to have a small amount of current that can flow through because this switch is held closed by the hydrogen gas. And that smaller amount of current, there's a resistor there to keep the current somewhat low. So it's looking for a low current all the time. Okay? When that pressure increases, that pushes this switch closed, which is the position it's shown in, And what's going to happen to our current? It's going to spike way up. So when it gets a high current, it says, okay, something has heated this loop up, and the pressure's increased, so there's a fire or something else. What happens if we lose our helium gas in here? If we get a hole in one of these, it gets hit, you close a cowling and it hits it, it nicks it, puts a hole in it. What's that? Hey, what? It's not going to work below the pressure, but we want to know that that's happened, right? So this integrity switch, which is normally held closed by the gas pressure, it will open if there's no pressure in here at all because of a hole. So now there will be no current flow at all between the two leads, right? So under normal circumstances, there's always a low current flowing through, going through that resistor. If all of a sudden the current stops flowing, that's a signal that the gas pressure has been lost altogether. And now the indication computer, indication logic circuits will provide a caution that the fire loop's no longer working. Okay, so it's that's part of that design. It needs to be robust, and it needs to be able to indicate. It needs to be able to indicate if it can't indicate a fire or an overheat. Okay, some of the other things we have, spot sensors. You worked with these. You saw ones like this that you put flame to on the top right. There's another version, a little smaller. This one's actually a thermocouple style right here. It's got you see the red and yellow wire. This one with the 3 wires is a switch. But you have thermal switches up top here. And the way those are normally put together is in a parallel indication. So if any one of these thermal switches closes, in this case, it'll send a ground back and turn on our indicator light. Okay. The other style that's shown here is a thermocouple, and these are in series with one another. And what they'll essentially do is as they heat up, what does a thermocouple do? It produces a little bit of a potential of voltage. It's enough, in this case, there's a sense relay to trigger this relay, closes this switch here, and then here's your hot, remember you have to have a hot junction, cold junction, then you end up with different junctions, right? That'll send a signal to turn on this very, very sensitive relay will turn on a bigger relay, and that'll turn on your indicator light. Okay? Using something called a Darlington pair of relays. Or it can, newer versions of these, what do you think they use in place of these relays right here? Solid state. What's a solid state? What's replaced relays in a solid state circuit? Come on. Basic electrical here. The logic gates are just a way of describing logic. It's a type of semiconductor. It's got 3 wires hooked up to it. A base, an emitter, a collector. What am I describing? It's a transistor. So a lot of these sensing relays have been replaced by transistors now. Okay? So, but that's the key. The big difference here is thermal switches typically have to be wired in parallel. If you had your thermal switches wired in series, they would all have to close before it sent a signal, right? If I got a thermal switch there, and one here, and one here, and one over there, and someone lights a fire under the window, right? We're not going to get an indication because all the others are open unless they were in parallel with each other. And then this one, or this one, or this one, or that one over there can trigger it, okay? Whereas the thermocouples like this, if this one on the left is creating a voltage, it will pass through the thermocouple here on the right and be able to trigger that. Now, what you're seeing with a lot of these thermal switch ones nowadays is they aren't even wired in parallel. They're all wired individually back to the computer. Because it's become really cheap to monitor a bunch of switches using a computer, basically. Why do that rather than having them all in parallel like that? Where does that make your job easier? What's that? You're on the right track. Who said troubleshooting? troubleshooting. So we had, the older planes I worked on were set up like this. Maybe the right wing overheat switches were like this, and the left wing overheat switches were like that. We'd get a thing saying, hey, there's a stuck switch in the right wing. The wing is 40 feet long. There's 15 switches in it. And to get to them, you've got 3 panels. Each panel, the outboard panel had 600 screws in it. The inboard panel had over 400 screws in it. And you got to figure out where is it a thermal switch in the inboard panel or the outboard panel? Well, you better hope you choose right, because that's 400 to 600 screws. And if you choose wrong, it's 1,000 screws, right? So now the newer versions is they wire each switch back, and you go into the maintenance computer. You can look in your maintenance computer, and it will tell you switch number, right-hand number 2 is the one that's triggering. Okay, I know exactly where that's in. That's in the inboard section of the wing. It's the second switch. You can find it a lot easier. So for maintenance purposes, they've gone away from a lot of these parallel designs, and they're discretely wiring the switches so that you can troubleshoot them easier. Okay. We had bleed leak detection were loop systems. One of them had 6 loops that went from the engines and APU at the back all the way up to the wing root, which meant they were in the aft equipment bay. They went underneath, our cargo was behind the passenger cabin. They went underneath the cargo floor. They went underneath the passenger floor. They went up to the wing box. They came out into the gear bay, and then they went to the wing before it switched to the wing detection system. And they were all wired together. When we had one of those bleed loops fail, we hoped and hoped and hoped it was one of the ones back in the aft equipment bay. But 9 times out of 10, it was one of the ones under the cargo floor or under the passenger floor. If it wasn't in the tail, we hoped it was in the cargo bay, because then we just pull up floor panels. If it was in the passenger floor, if it was under the passenger floor, now we have to remove seats, we got to remove carpet, and then we can start to remove the floor panels. But we had no way of knowing where it was, other than you could go and disconnect them at certain spots and see if you could figure out which way it was. So we'd break it at the between where it entered the pressure bulkhead. We'd break it and okay, hopefully we see the fault back here in the tail somewhere, because they're a lot easier to get to. Other sensing devices, smoke detectors. There's 2 main types: light refraction and ionization. And so for these, light refraction is basically there's a beam of light in there and a light source, a photoelectric cell to pick it up. When smoke goes in, it refracts the light, basically blocks it, scatters it. And so the amount of light going from the source to the photoelectric cell gets dimmer, and that tells it that there's a fire. This is how most of your ones in your house work, although some people have probably seen the little radiation symbol on them. If they have the radiation symbol, they're an ionization type. And so in this case, what you have is a couple of charged plates with some kind of a radioactive material, and that radioactive material giving off charged ions will hit the plates, and there will be a certain amount of radiation going and hitting those charged plates, which produces a current. The smoke in this case now, essentially the smoke gets between the radiation source and the charged plates. Less of those ions coming off of the radiation source bounce into the plates and reduce the amount of current being produced in those plates. Okay? And so you'll see, and those will have the little radioactive symbol on them like that. Okay? And there are home smoke detectors that have these, although they're few and far between nowadays. But the ionization tend to be a little bit more sensitive, and so they're used a lot more often in aerospace and aircraft, where we can kind of control. The biggest thing is control the disposal of them. You send people, people buy these for their home, they stop working, they toss them in the trash. Airplanes have them, they stop working, they get overhauled, they're dealt with more, more dealt with properly than being just tossed in the trash. Flame or infrared optical sensors. This is another style out there. You saw the style where it's kind of the cylinder with the big lens on the end of them. These are going to see emitted heat from a fire, or the big key is they can see smoldering material. So they can actually see a fire forming before it becomes a fire. Okay, and that's their big advantage. You don't have to wait until there's enough smoke to trigger a smoke detector. You don't necessarily have to wait until there's a ton of heat to trigger a fire loop or a spot sensor. These are just looking out into, say, a cargo bay, and if they see a bunch of infrared energy being emitted from something, they assume that it's a fire or something hot. Now, you have to be sure that they're not pointed at something like a heating duct, right? Or even things like, well, not such a great example, but back in the day, things like fluorescent lights gave off a lot of infrared radiation. They got hot, anything that gets hot, okay? So they can see something like, say you pack that lithium ion battery in your suitcase and it starts to go exothermic. Something like this would be able to pick up the heat inside of a bag. Your bag would start to get warm. These would be able to pick up that heat signature before it actually burst into a full-on fire. Okay. They're also used to monitor things like gearboxes sometimes. So on some helicopters, they have these pointed at the gearboxes, and if you start to get a gearbox that's overheating, getting ready to shell out, it'll be able to pick up the fact that the gearbox is running hotter than what it's supposed to be. Here's our carbon monoxide, simple ones, chemical type. You've seen these in small airplanes. Bigger airplanes, if they need them, which is few and far between, again, more of a cargo thing that's carrying stuff where carbon monoxide could be emitted. They're going to be an electrical sensor. They're not common because our bleed air is pulled from the compressor prior to any kind of combustion taking place. And so there's really not a chance of carbon monoxide getting in there. But they sense the concentration and the time of exposure. So a small amount of carbon monoxide over a long amount of time can be just as deadly as a large amount of carbon monoxide in a short amount of time. The reason for that, when you breathe carbon monoxide, it binds to the hemoglobin, the oxygen carrying part of your blood, and it doesn't let go. And so as it binds and binds and binds, it prevents your blood from being able to carry oxygen. But when it comes back to your lungs, it doesn't get breathed out like CO2 does. And so it's bound too tight to break back away and be breathed out. So that's why a small concentration over time can build up in your blood, or a large concentration over a short period of time can be just, either one can be just as deadly. So they're monitoring concentration and exposure time. And then our combustible mixture mainly are going to sense the concentration of oxygen and then whatever our fuel source is. And it cannot, however, sense if there's an ignition source, right? We need fuel, we need oxygen. Just fuel and oxygen doesn't mean that it's going to cause a fire. It has to be ignited somehow. But these are not going to be able to tell you that. They're just going to say, hey, there's a high potential that if an ignition source comes about, that it can cause a problem.